and first of all, many thanks to the organizers for having me here and for this very nice workshop. And I will talk about aspects of quantum simulation of the Fermi-Hubbard model. And before I really start, I just want to use this opportunity to draw your attention to the Munich Quantum Valley Initiative. I mean, just flash this very briefly. So basically, this is the idea of bringing together some groups in Munich to actually build a quantum computer, so to say, but not only the, let's say, the physical, like a physical quantum computer, but also the accompanying software stack, so to say, and of course also algorithms, work on algorithms and so on. So it's, I would say it's like a very interdisciplinary endeavor, and it's also working out, I would say, relatively well in the sense of that it brings groups together which maybe usually not directly talk to each other, for example, and also looking into, as I said, like software stack, how do you make this accessible in the cloud or so, and so on. Okay, and one of the things which is coming out of that is a spin-off called ThanQC. So this is basically trying to use neutral or ultra-cold atoms to build a quantum computer. So it's very, I guess it's very similar to QEra from Boston and from Pascal in Paris, I think, so also using ultra-cold atoms. And just coincidentally, so this is coming out from the Immanuel Bloch's group. It's MPQ in Garching, so Max Planck Institute, and this is coincidentally also the same institute where Ferenc Krauss is, who was actually awarded the Nobel Prize today. So okay, but now let's actually jump into the topic. So I'm basically, my talk is partitioned into two parts, and the general motivation is quantum simulation. So we just want to approximate or basically perform the time evolution of a given Hamiltonian. And what you see here is basically one of the, I mean, this is from 2019, or actually the experiments from 2018. So one of the earlier works where they just, this was actually in the group of Frank Pollmann and Johannes Knolle, where they tried this, basically just a Trotter splitting, tried this out on a physical quantum computer. Of course, this was just a toy model system, right, like 6 qubits, but just to see that at least qualitatively you can use Trotter splitting and really put this onto a physical quantum computer and get some, well, it's still quite noisy, but you get some at least qualitatively correct results out of that. Right, and of course, I mean, as we have seen, or as is clear, that this is still, let's say, the most natural way, I would say, to implement time evolution, just because, in the sense of this kind of Trotter splitting of a Hamiltonian, because you don't need any auxiliary gates, and it's just anyways, it's what quantum computing or quantum gates are, right? So really, it's a time evolution of some underlying quantum system. So it's really natural to do this in this way. And in the first part of my talk, I will actually talk about kind of an error analysis of this Trotter splitting. And this is very much in the sense of this commutator scaling paper from Childs. And the second part is actually how to further improve on Trotter splitting methods. So this is more like a classical optimization in the sense of if you have a Trotter splitting, you can even make it better, so to say. Okay, but let's start with the first part on, let's say, this is more like an analysis of errors. And as I said, it's basically commutator scaling. And what I will also show you is like a specialization to the Fermi-Hubbard model. Okay, so I mean, you have probably seen this in one way or the other. So basically, the starting point are these Lie-Trotter product formulas, and the simplest instantiation of this idea is that you have like a Hamiltonian which is partitioned into these A and B terms, and here we assume we have like an even-odd splitting. So basically, assume you have a 1D system, and the Hamiltonian consists of hopping terms on a 1D lattice, and then you just partition them into this even to odd and then odd to even hopping terms. And the point is that these ones don't overlap. I mean, they have non-overlapping support. So you can basically, if you convert this to quantum gates, you can apply these gates in parallel and exactly in principle. Okay, and then you have, what the Trotter splitting does, it approximates the true time evolution at least in the lowest order by these two matrix exponentials of A and B separately, and then this gives an first order method, so to say, but there are also higher order generalizations possible, right? So this is all, well known, so to say. And I also want to give you an idea versus, I mean, the name is called commutator scaling, right? And I just want to give you an idea where this comes from, so to say. So in this subsequent error analysis, where do commutators appear? And okay, this is kind of the simplest version of that. So if you just take the time derivative of this first order method here, it's just doing it explicitly, then we can basically add this A term here in front and then subtract it, and I have hidden this, so to say, inside this commutator. So the orange brackets is a commutator, right? And then I write this formula in such a way that the time derivative of this S is basically minus IH times S. So this looks a bit like the Schrödinger equation, and then times plus some additional terms. So if you just now use this variation of parameters formula or apply this to this relation, we get something like that. And finally, we can express this commutator here inside the integral again as an integral, so to say. So basically, we use this exact relation that commutator of e to the tx and with y is the same as this expression on the right. But okay, anyway, so if you just do this algebraic manipulations, you see that in the end you end up with some integrals over some commutators of this x and y, or this a and b's basically. Okay, so far so good. And now the first result I want to show you here is basically, as I said, this builds a lot on this child's work here. It's basically a generalization, slight generalization of this, let's say, error terms. So this is what we derived in this preprint here. And it looks, okay, the formula looks a bit, busy, so to say, or complicated, or tedious, but okay, let me just give you the main idea here. So I guess the important part are these, these adjoints here. So add here means just the commutator. So adjoint A, B is the commutator of A and B. And we can also take powers of that. So adjoint A to the power of 3, B is then a nested commutator. And in this, on the right here, basically we have a lot of expressions involving these nested commutators essentially, and some multinomial coefficients in front. But this is kind of, that's it. So basically what we have is the spectral norm difference between a general, could be an higher order Trotter splitting method, and the true time evolution is bounded by this whole expression here. And sorry?
What does small prefactor mean?
Oh, sorry. This is just nomenclature, so to say. It's more like saying, we explicitly give the prefactors. Or we try to have a sharp bound, so to say. It's just a nomenclature which we actually also took from the paper here. Okay, but maybe you can just, it's not really, how should I say, hopefully it's not misleading. What I just mean is that one can explicitly write down the prefactors or the bounds, right? Because they also give a general bound, which is just saying like up to some constant, but here we also want to work out what are the constants in this error bounds.
In the Child's paper, if I remember correctly, they have a general derivation, and then they have a more specific derivation, which is the alternate due to Lubitsch, and the second one has a smaller version. That's the same.
Yeah.
I wonder if this setting, what is small.
So basically, we generalize this what they call small prefactor. So it's a slight. So this formula is basically a slight generalization of the results in the Child's paper, but it's using the same techniques basically. Yeah.
Is it fair to say that these are more or less explicit factors?
You could also say that. Yeah.
If you look at that term,
Yeah.
often they're integrals and they're much harder.
Mm-hmm.
Right? If you write every think in terms of integrals, you can also write formulas, but then you don't see anything.
Yeah, yeah.
So more or less explicit.
Okay, yeah. Let's call it explicit prefactors here.
So it doesn't matter that you're dealing with the Fermi-Hubbard.
No. This is very general, right? So the Fermi-Hubbard will come later. Yeah. Right, but the point is, we have also implemented this that you can actually explicitly evaluate these terms. But okay, what you need to do is, of course, to really get the coefficients here, you need to evaluate these nested commutators and also the spectral norms of these. Right, this is more the technical challenge to actually do that.
Is this bound tight?
No, probably not, because you have some in between you have some, I will also show some examples where we compare it with, let's say, exact computed error, and this is not tight. Yeah.
So since we're at that, if you assume that all your ingredients have norm less than 1, that probably still grows polynomial or something to the power p, right? I think if you sum it then all up, it looks like this goes like a constant to the number p. Right? It looks like it, but there's so many terms to tell it from here.
Yeah, I'm actually not sure about that, but maybe let's see. We did this explicitly for the Fermi-Hubbard model to have okay. So this is actually the next point. So basically what we do next is we specialize these things for the Fermi-Hubbard model, and just the usual. These are again these fermionic creation annihilation operators, and I've drawn this for a 2D lattice, but basically, spinful Fermi-Hubbard model. And for later reference, we will use this. So this Hij sigma will be the hopping term, so kinetic hopping term between two lattice sites. N will be the number operator, and we also have a signed hopping term, which is basically just the H tilde, which has a minus sign here. So this will appear later. Okay, and I will start with the one-dimensional lattice, but we will also do 2D lattices. So I guess the most straightforward splitting. So first of all, the first step which you do is you split the Hamiltonian, and basically we just have to partition the kinetic terms into even odd and odd even hopping terms, and then we still have the Coulomb or interaction term basically. And the point is that I always write this as a sum, like this outer sum is over some sublattice lambda prime, and this will also be relevant later on for actually evaluating these nested commutators. Okay, but here's again a visualization of this H1, H2, H3 here. Okay, and here is lambda prime is basically every other lattice site. And now, now we actually, the technical part here in this work is basically we still need to evaluate these nested commutators, right? But the point is we can first of all analytically do this for these elementary operators, right? If you just have, for example, number operators, okay, say anyway commute, but then you can just with pen and paper, so to say, pre-compute these commutators between these elementary hopping or number operator terms. And but the nice thing is, which is maybe not obvious, if you nest them, this is still a closed system in terms of sums and products of these number operators and hopping operators. So we'll never, let's say, fall out of this. You could call it the algebra, so to say, of these operators. So what we still need as ingredient, so to say, is this relation that if you have a commutator of a sum, okay, it's the sum of the commutators, and if you have a commutator of a product, you can also expand this in this way, basically. But as I said, it's kind of a closed system, so we will always just have sums and products of these elementary hopping and number operators, which is like useful for actually implementing this later on. Okay, and another trick which I'm using here is that if you have such a so what we will need is basically that the terms are are just sums over lattice translations, or this sublattice lambda prime translation. So this is this outer sum which I mentioned before. And when we implement this in the end in some Python program, I mean, we don't want to store an infinite sum, so to say. So we just store one instance and implicitly assume that we still have to take this sum over the sublattice lambda prime. And now we just use this, let's say, simple identity that if you have a commutator of two of these sums, you can just write it like that. So you just move one of the sum to the outside, and then you just, basically what you need to compute in practice is a commutators of AI with translated copies of the BI, basically, right? Well, and this is all implemented here in this, it's a Python toolbox, basically, which does this more or less symbolically, right? So it was also, let's say, fun to implement this because it's more like a, like a microscopic compiler, you could say, in some sense, because there's also a simplify function there, or of course we implemented these commutation relations, but it's more like a, like a transformation of expressions, or like a mini symbolic toolbox, so to say. Okay. Just to give you an example how this looks like, right? I mean, here's a nested commutator with 3 Hamiltonian terms. So remember, H1 was one of the hopping terms, and H2 the other one. And then, well, you get such expressions out of that. Well, I think it's not really relevant what these are explicitly, but the point is also that you see if you have, especially when you have higher dimensional lattices, this gets very tedious, so to say, to do with pen and paper. So it's probably good to have some computer program to do this automatically. Okay, and then for this particular example, what you get here if you evaluate the spectral norm is just this 4 times v to the power of 3. And in our implementation, I mean, for example, we have some, we use a trick that if you have a term which only consists of quadratic, like it's quadratic in the fermionic creation annihilation operators, then it's basically a free fermion operator. So, and then you can just easily evaluate its spectral norm, so to say. Because, like, if you imagine these are, like, for such a term, you would need to really, or what we do in the end is we really represent this internally as a matrix, and then compute the spectral norm of this matrix. But this only works up to a certain, let's say, involved lattice sites in this expression. If this gets it has too many lattice sites, you can't do this exactly anymore for practical reasons. Okay, but in the end, so what we get for a one-dimensional lattice and strong splitting is this bound, so to say, and this is kind of the first result of this project. So you kind of, well, it's a very explicit expression, so to say, and the v is a coefficient in front of the kinetic term in the Hamiltonian, and u is a coefficient in front of the interaction term of the Hamiltonian. But it's nice that it's a relatively compact formula in the end, so to say. Okay, and well, since this framework is relatively general, we can also do it for, let's say, a 4th order or higher order method. So here's a result for the 4th order Suzuki method. And what I also show here is basically what I mentioned before, a comparison with, let's say, true error, right? So what you see here in the solid or continuous line is basically the error of the Trotter splitting compared to the exact time evolution or numerically exact time evolution. But this is on a small system size, like system size 4, just for practical reasons, because otherwise you can't really compute the numerically exact time evolution operator. And the dotted line or dashed line would then be the bound, and you see that it's still not sharp, so to say. So it overestimates the error. Okay, it would be a bit strange if it would be below the solid line, right? But no, anyway, but it's not coinciding with the solid line, right? So it's not a sharp bound. And also one maybe slightly interesting observation is here that so these green and orange lines are 2 4th order methods, And you see that our, let's say, error analysis would predict that the orange one has a lower error, so to say, but the empirical error is, the ordering is reversed, so to say. So the green one would perform a bit better than the orange one, so to say. This is also, well, turned out, I mean, I don't have a good explanation why this came out like this, but anyway. And maybe what is also interesting here is that the bound is a bit sharper, so to say, for the second order methods as a blue curve compared to the fourth order methods, which is, I guess, due to the fact that you have just more of these nested commutators. Yeah.
Question. Is there if you do symbolically, I would guess that the number you get will be something like the integers of rational numbers. If you get these numbers are a little bit random, is that where do they come from?
So we also have, I guess it just comes from the fact that you have to, let's see if I go back a few slides. I mean, the norms of these nested commutators might not be integers, right?
Okay, there might be some future complicated rational numbers.
Yeah.
Yeah. Okay.
Right. I mean, it's a good question. So whether this is still right, if these are still rational numbers or whether these are just really, irrational ones, I don't know. I have to say, yeah.
So it seems that you're doing very careful analysis, right? But still there was this overestimation. So do you think this is coming from like triangular inequality, or where actually does this discrepancy come from?
Basically, because you have a lot of, when you do this derivation, you basically, you apply the triangle inequality, yeah. So that's just overestimating it, I guess, yeah.
So that's why you higher order because there are more terms, so that there are more triangular inequality terms.
Yeah.
So actually, I don't understand the question of rational numbers. Like, why can't you choose one rational number slightly bigger than this numbers that you have here?
Can you repeat the question? Can you say it again?
I'm trying to understand the context of this rational number question about these coefficients. So why can't you just choose a rational number just a little bit bigger than whatever numbers that you have here?
I mean, the numbers here are basically just what comes out when you evaluate this expression here. But basically with the nested commutators for the Fermi-Hubbard model. And I guess the norms here, they could be irrational numbers, right?
Yeah, but why do you care about that?
That was my question, sorry.
Okay.
Yeah. No, one curious observation is also that some of these coefficients are really orders of magnitude different, right? So here, this one is really small, and the other ones are kind of, so they're relatively big differences. But I guess let's say for the Fermi-Hubbard model, if you make U large, right, then this would of course also blow up again, right? Okay. So far so good. And then, as I said, we can also do this for, in principle, for other lattice geometries. So here I show you just 2D lattice and also the corresponding, like the chosen partitioning, so to say. So this would be the equivalent of the even-odd partitioning in 2D, so to say. And then again, here would be the results in the end. And what you see here is that the coefficients are actually also quite a lot larger compared to the one-dimensional case. I have to admit I didn't put too much thought into like if whether there's a good interpretation of the magnitude of these numbers, but I mean this is basically what comes out of these calculations.
Yeah. Why is there no in the first case like a u cubed, and then the second case a u to the fifth?
That's a good point. Yeah, because u to the power fifth would mean you just have a commutator of the interaction term with itself, but the commutator with itself is 0, right?
But that's not the case for the kinetic part.
Yes, because you have two different kinetic terms, so to say, right? You have like this one, and they don't commute with each other, right? But of course, the interaction term, it commutes with itself, and so there's no u to the power of fifth term here. Yeah. That's that's a good point. Yeah. Yeah.
So I realize you just said you haven't talked much about this, right? But 92 is much larger than a lot of these other ones, right? Is there some sense in which I can interpret this like this is some particular physics process that involves multiple hopping and interaction that gives rise to this? Asking you to speculate a little bit.
Yeah, I don't have a good interpretation of that. I mean, so maybe the only thing which you can observe is that if you, let's look at this v to the power fifth term, right? So this means just you have commutators of the kinetic terms with themselves, and this would always generate just other, let's say, it would still be a quadratic operator. And whereas here, when you have the u in there, you also generate, let's say, higher ordered fermionic operators, like, for example, powers of 4 or something. But the same could be said for this one, right? So I don't know why this one comes out much smaller than this one.
Yeah, but I mean, maybe like this is double exchange and some hidden form.
Yeah, right.
Like that.
Yeah, it's a good point. So maybe one should actually spend a bit more thought on, or try to have some rational understanding where this comes from. Yeah.
Question?
Yeah.
If you consider both Hubbard model instead of Fermi-Hubbard model, how does this the formula change, the error changes?
Sorry, can you say it again?
If you consider both Hubbard model,
Oh, the Bose-Hubbard, yeah.
how does it change the error?
Well, I mean, so as I said, like this general formula is independent of the particular Hamiltonian, right? So what you would need to do for Bose-Hubbard is basically, let's say, do this exercise of evaluating these commutators again, and then I guess you would have also, like for the fermionic number operators, the spectral norm is 1, right? But for bosons, this could be larger than 1. So you would have other,
So do you expect that the error formula changes, or?
I mean, admittedly, I'm not sure how, like, qualitatively how these coefficients would change, but I mean, they would certainly be different, right? But I don't really know on top of my head how they would change exactly, right? But it would also be relatively, let's say, straightforward to implement a bosonic Hamiltonian as well, right, in this framework.
Number, I mean, here you explicitly use that the equation not actually they're bounded by 1.
Yeah.
Okay.
Right. You need to, right, for bosonic you would need to, that's also a good point, right? You need to, like...
Yeah, the operator norm and the vector norm, they have a huge difference. Right, yeah. So you can't even bound this beforehand. I mean, another thing which might be interesting, but which we didn't do here, is like if you really consider the initial state or so in this analysis, right? So which input state you have. So maybe for bosonic Hamiltonians, you can't really have a meaningful bound, like as Lynn just said, right? Because they're not really bounded at all, right? These number operators. If you admit an infinite or arbitrary occupation number.
Yeah. So both Hubbard model, we know there's like quantum chaos behavior as opposed to Fermi-Hubbard model.
Yeah.
So that's another indication.
So you could maybe do Bose-Hubbard with some cutoff, so to say. Yeah. Okay. And finally, so just for completeness, we also use a triangular lattice. And here, I mean, the hexagons are basically, these are again these sub-lattice points. So the blue arrows are the unit vectors, so to say, of a sub-lattice, this lambda prime, and all the individual Hamiltonian terms are then translation variant with respect to this sub-lattice. So with respect to the hexagons. And so here the red triangles would be, let's say, one. So basically here we're using 3 kinetic terms, and the red ones are just the instantiation of one of these kinetic terms. But then you have also rotated copies of that. Okay, and here again the numbers are again very much larger though. But as I said, I don't really have a good understanding intuitively where this comes from. Okay. Yeah, so this was basically the first main part. And if there are no immediate questions, maybe I can go on with the second part. So this is now basically switching gears in some sense. And now we assume, okay, we have a Trotter splitting error. We have some kind of time evolution method. And can we make it even better in some sense? Well, and the idea is also relatively straightforward. So basically, we just so let's say we have this exact time evolution operator in this right box, and we use a brick wall ansatz circuit, or this kind of circuit layout consisting of 2 cubic gates, and to approximate as well as possible this true time evolution operator. And the topology of this circuit here would be typically given by some Trotter scheme, right? So we know, let's say this could be some even odd splitting, for example. So we know which gates there are, but what we still allow for is basically optimizing the entries of these gates. So this is kind of the task, and we do this on a classical computer, right? So basically the idea is to classically optimize these G's to achieve a good approximation error, so to say. And we also assume here that this is translation invariant, so which will become important later. So you see that in each layer there's the same G basically. So there's G1 in the first layer, so this G1 is repeated, so to say, and the other G's are also repeated. Okay, and we minimize here the distance, by the way, with respect to the Frobenius norm. And we, of course, one important thing to keep in mind here is that these gates are unitary matrices, right? So this is also, let's say, conceptually a bit different from other works where you could also treat these gates as just parametrized gates, right? Let's say it's like some rotation gate, for example, and then you just optimize the parameters of the rotation gate. But here we explicitly say that we don't assume any parameterization. We just treat them as matrices, but of course they have to be unitary, right? So, and then the question is, how do we do this in practice, so to say? But before I come to that, I also want to mention or say a few words about this translation invariance. So, so this has to do with this light cone considerations, basically, because the idea here is to optimize, or let's say what we hope to do is to optimize the quantum circuit for a small, relatively small system size. But then you can just use it for larger systems by just copying the gates, right? So if you go back one slide, right? So basically, for example, I just use this small system size to optimize the gates. But if I want a larger system, I can just take copies of the same gates, right, to make it larger. And of course, the question is, why is this reasonable, or why does this make sense? And the intuition, at least for me, is the following: that you say, okay, so what you see here as yellow is basically this light cone of the physical correlation. So this would be how the, let's say, the influence of this cube, or how this lattice site could influence some other qubits as time progresses, but for the true time evolution, right? For the actual Hamiltonian. And okay, and the wires which are here in bold red basically are the ones which can be causally connected due to the brick wall layout, right? So for example, this qubit here can never directly talk to this qubit up here at this time point due to the brick wall structure, right? Because they're not causally connected, so to say, in the brick wall layout. But now the point is, if I choose a system size which is as large, at least as this extent of this light cone here, then, so to say, I don't need to. Yeah, this is efficient because if I use if I can just extend it to larger systems, because the causal influence will not be experienced, or what will not be felt by the qubits which are far away anyway. So it's fine to use a smaller system for the optimization. Does this make sense? Yeah.
Do you know for which age the time the cone is actually accurate to assume? Because there might be other ages which do not have causality, right?
Yeah, right. So this, of course, this assumes that there's some, let's say it's a local Hamiltonian, essentially, right? It doesn't have to be a nearest neighbor Hamiltonian. It could also be second neighbor or something, second nearest neighbor, but it still has to be, let's say, local in some sense, right? Of course, if you have all-to-all connectivity, then this argument would not hold anymore, yeah. This is, of course, some assumption which we put in. And, it's also, let's say, what you should keep in mind is that time for which we optimize this whole thing is, you should think of this as more like a time step, so to say, not a full evolution time, but more like a time step of a, let's say, Trotter method, or for example, because if you want longer times, then you of course just repeat the circuit. So conceptually, this is just a time step. Yeah, so far so good. And then, okay, I mean, the next point is a bit like a technical way of, okay, how do we actually do this in practice? So first of all, we define a target function, so what you actually want to minimize. So as I said, we minimize Frobenius norm distance between the brick wall circuit and the true U, so U would be the true time evolution operator. And if you just expand this Frobenius norm difference, you see that you have terms with U dagger, but these are just identity because U is unitary. So this minimization is equivalent to minimizing this F here, which is basically just, let's say, trace between U dagger and W, right? And if you write this expression as a tensor diagram, it would look like that. And this, periodic connections are basically just due to the trace. So this is our, let's say, tensor diagram, which we want to minimize with respect to the G gates here. And and now the funny thing is, if you compute gradients, right? So you basically just cut holes into this tensor diagram, right? So if I compute the gradient of this with respect to GL, I basically take the sum of all sum of the same circuit, but where I omit one of the GLs from the circuit, just by, you can it works basically as if you had variables and you just take derivatives of a, let's say, of a polynomial, right? Maybe it's good to think of this as a polynomial where it just takes the derivative of a polynomial. Yeah.
Does the Hamiltonian need to have periodicity or locality in order for this to work well?
We assume that it is periodic because, to be able to use the same GL, so to say, like just copy the same GL. Otherwise, this ansatz would not make sense if the Hamiltonian is not periodic, right? I mean, so I guess the overall framework would also work if the Hamiltonian is not periodic, but then you would need a different G in each position, so to say, right?
And then what about locality?
Locality is kind of important for this light cone idea, so to say.
Like the Hamiltonian also has to.
Has to be. Right. Otherwise, at least this intuition would break down, I guess. Yeah. Okay. So far, so good. And then, technically, maybe let's go to as I said, like this idea of taking gradients, right? If we just take a gradient here, I basically cut holes into this tensor diagram.
How do you implement the E to the IH? Is that simulate?
You mean the reference? You do it just numerically,
Just do numerically, using Trotter.
Or no, you just brute force matrix exponentially.
Is it possible for the Hamiltonian to be geometrically local, but the gates are non-local?
Sorry, what is non-local?
Does your method apply to the case where the Hamiltonians are local, but the gates, the quantum gates are non-local?
This would also work. Right. So I mean, right, we could also have gates which are not nearest neighbors in this particular ordering of the qubits, so to say.
So as an end goal, do you expect that this variational circuit, in terms of step, would be linear in T or independent simulation T?
It should still be linear in T. But T for, conceptually, T is here more like a time step, so to say. So we fix T and keep it also small, so to say. And then if you need longer times, of course, you just repeat the circuit.
But then as if for some age, Lex laboratories have worked out this thing, so which the depth is independent of T, so that's automatically better. For certain age.
Okay.
Not Fermi-Hubbard stuff.
Okay. Okay. Yeah. So maybe for special cases, yeah. Okay. So I would say the technical part then in this work is more or less like how do you actually get these gradients when you work on this manifold of unitary matrices, right? Because this is kind of the only condition which we have on these G's that they are unitary. And then of course you can just, like what you do in practice, you just compute the gradient first as if it was a general matrix, but then you need to project this matrix onto as a gradient onto the tangent plane. So symbolically you can really, or pictorially you can imagine this like that, right? So here this manifold would be the manifold of unitary matrices, and we basically want to stay on this manifold, and if you compute gradients, for example, you stay in this tangent plane. So it's a bit technical in the end, but I mean, I would say conceptually the ideas are very are not so complicated. And there's also this nice book here, right, which I've referenced here, which gives a very nice, let's say, introduction to this topic. Okay, and then finally, I also want to mention that we use the Riemannian trust region algorithm to actually do this optimization. So conceptually what you do is we do not only do, this is maybe important that, first we just tried gradient descent, right? Because this is probably the simplest thing you would come to your mind, right? You just take gradients, do gradient descent to optimize these gates. But it turns out it's like you basically obtain better results when you use something like a Riemannian trust region algorithm. And the idea of this algorithm is basically that locally you approximate in this case, your target function up to second order. So you also need to compute Hessians, right? And this is a bit, as I said, in technical terms, this becomes a bit tedious to do, but it's conceptually it's not very complicated. And then, okay, you have a second order representation of your target function, and this Riemannian trust region algorithm then basically finds the true minimum of such a function, so to say, as if you only had up to quadratic terms, so to say. But this is all, I would say, well established, right? So basically, we have literally implemented this algorithm, which is taken from this book from Upsil, right? This trust region algorithm to optimize the gates essentially. And maybe one interesting point here is also that we optimize all of the gates simultaneously. So not one by one, but really simultaneously. Okay, and the retraction here is basically what you need to go back to the manifold of unitary matrices. Because if you move along the tangent plane, you go slightly out of the manifold, and then you have to project back onto the manifold. And this is done by the retraction, which is just you do a polar decomposition essentially. Okay, and all of that is implemented here. Just straightforward Python code. And finally, I just want to show you some numerical results of that. So we applied it first to the transverse field Ising model, which is just one of the simplest models, I guess, on a 1D lattice. So it looks like that. So it has some these set terms, which you could interpret as interaction or hopping terms, and then this external field term here. And Z and X are just the usual Pauli matrices. So we just choose some parameters, set the time step to 1, and we optimize this for system size L equals 6. And here I've shown you just optimization progress, so to say. If you iterate, in this case it converges relatively quickly, and basically the orange line would be the rescaled f, what they call target function, and the blue curve is the spectral norm error. But for this particular example, and this is now this plot in the middle, it worked, so to say, surprisingly well. So a bit better than what we expected. So what you see is basically here, the blue curve would be the error after our optimization. So this would be our method. And on the x-axis, you see the number of circuit layers. So basically the depth of the quantum circuit. and on a log scale, right? So, and here on the y-axis you see the spectral norm error, and these other curves here are the errors which you get from the usual Trotter splitting methods, right? Which people would typically use, like for example, strung splitting is this orange line, and I mean you see that you can really gain a lot, right? Like this is really, you know, you get the same precision as strung splitting by basically going from, there should be 5 layers compared to something like 50 layers for strung splitting, right? So there's a factor of 10 reductions the number of layers which you need for this case, right? Okay, you can also use higher order methods like this. This one is an order 4 method, but you still see that the optimized circuit performs much better, so to say, in terms of, okay, either you need less layers for the same accuracy, or you just get a better accuracy for the same number of layers. Okay, and finally on the right I show, so now we come back to these light cone considerations. So what we did here as a numerical test, so to say, is that, okay, so now we use optimized gates, which we optimized for 6 lattice sites, and just use them for larger systems, but without re-optimizing them, right? Just use the same gates for the larger systems and plot the error. And the point is that the error hardly changes, right? So this is kind of a, let's say, at least it's not a proof, of course, but a confirmation of this intuition that if you use the same gates for larger systems, the error essentially does not change, essentially, right? So you can use that for larger systems as well. Yeah, so that's basically the story here. We also did this for the Heisenberg Hamiltonian, and I mean here you see the equivalent plots, and I mean, so one thing here is that actually does not work so well for this model, right? You see our curve is still below the other ones, but not so that, yeah, it's not so much better, so to say, right? But the point is, you could, I mean, in some sense, by construction, we can be better than any Trotter method which you can invent, right? Because we can always use the Trotter method as starting point for optimization and then optimize it further, right? So we can never be worse than any of these Trotter methods. Yeah, and here also this extrapolation to, let's say, to larger systems. If you use the same gates, but for larger systems, the error really, again, doesn't really change a lot. Okay, and then, yeah, this is basically brings me to the outlook already. So, okay, I haven't shown you the data for the Fermi-Hubbard model for this Riemannian optimization, but I mean, this is just basically we have the data. This was done in a bachelor thesis. I just haven't had time to actually plot this, but I mean, qualitatively, it's also very similar, right? So the results, or the qualitative results, are basically very similar. One thing we also want to, or have partially done, is think of how to make this run on HPC systems, in the sense of just optimizing the code. Let's say use caching, and this is also, I would say, very interesting by itself, how to, because there come in some ideas from machine learning, let's say, in the sense of use some kind of back propagation, but this just comes out automatically if you just want to reuse your computation results. Yeah, and then, of course, if you have a more, let's say, performant implementation, we eventually want to run this for, let's say, for example, 2D lattice geometries. And potentially also use non-unitary target functions, like let's say you do some kind of block encoding, for example, but this we haven't done yet, but this is on our mind, so to say. Yeah. Okay, yeah, that's it. So thanks. And
we got about 10 minutes for